Assalamu alaikum. Welcome to the next class. In this class, we'll be discussing about the loss which is associated with the corona. So this type of loss is known as corona loss. As we know that the ions that are produced by the electric field, it forms a space charge that moves around the conductor. So this space charge requires some energy so that these charges remain in motion, and this energy is usually derived from the supply system. So the space which surrounds the conductor that requires some energy is lossy. So in order to maintain the flow of energy over the conductor in the field wherein the additional energy would have been otherwise absent if these charges are not present around the conductor, so that means it becomes necessary to supply this additional power from the supply system. So this additional power that is supplied for maintaining this discharge is known as corona loss. So an experimental setup which is shown in this figure was arranged by a scientist named as Peak to measure this corona loss, but in case of DC. So he used a concentric cylindrical type of the conductor in which a DC source is connected. Over here a load is connected, and then he connected an ammeter over here. So at this point an ammeter is used which measures the current that flows from this conductor to this ground. So then the power loss, since it's a DC case, or we can say it is resistive in nature because power loss is a real power, the power loss will be given by VI. So the Peak, that is the scientist who actually discovered this loss, this gives us the formula to calculate the corona loss. He made a number of experiments to study the effect of various parameters on this corona loss, and hence he deduced an empirical formula. Empirical formula means the formula which does not have any derivation. So the empirical formula that is given by the Peak is this, that is P is equal to 241 into 10 to the power minus 5 F plus 25 divided by delta square root of R divided by D Vp minus V naught whole square, and the power units are measured in kilowatt per kilometer per phase. Since it is per phase measurement, you will see both these voltages will be phase to neutral voltage. F is the frequency of the system. Delta is the air density correction factor. This is the same factor which we have used to calculate the critical disruptive voltage. R is the radius of the conductor. D is the distance between the two conductors. Vp is the operating voltage, and V0 is the critical disruptive voltage. Two things you need to understand from this equation, that is 241. In some books it is written as 241, in some books 244, in some books 245. So you can choose this value as your choice, 241, 244 or 245. And the nomenclature for this Vp and V0, it changes from book to book. Some write this as V0 and some write this as Vd. V0 will be operating voltage, Vd will be this critical disruptive voltage. Some write this V and some write this Vc, where Vc is the critical disruptive voltage and V0 is V is the operating voltage. So you need to understand this, not looking at the nomenclature, just that this first voltage which is given in this square term is the operating voltage, and the second term is the critical disruptive voltage. So with this, one more thing that is regarding this equation, that the equation is derived for the fair weather conditions, because you will see that when the weather conditions are not fair, this critical disruptive voltage will change, and this power loss will also change because it is dependent upon the critical disruptive voltage. The approximate loss under foul weather conditions is obtained by taking V0, that is this V0, as 0.8 times the fair weather value. So critical disruptive voltage in case of foul weather is taken to be only 80% of the voltage which is actually in the fair weather condition. So what I mean to say is that actually it decreases, but to get any value, it has to be taken as 80% of that value. This empirical formula that is derived by the peak has certain limitations. This gives the correct results only for the frequency which lies between 25 and 120 Hz, and the conductor radius should be greater than 0.25 centimeter, and also the ratio of Vp by V0, that is this Vp by V0 should be greater than 1.8. So if there are other frequencies, or if the radius is less than 0.25 centimeter and if Vp by V0 is less than 1.8, there is another formula known as Peterson formula which gives better results than the Peak's formula. It is given by Pc is equal to 2.1 f Vn divided by log 10 log to the base 10 d by r whole square multiplied by 10 to the power minus 5 into capital F. Its unit is also same, that is kilowatt per phase per kilometer. So Pc is the corona loss, F is the frequency, Vn is here the RMS voltage, that is the phase voltage, which in the earlier case it was denoted by V0. So d is the distance spacing or equivalent spacing between the conductors, r is the radius of the conductor, this should be in meters, this is in meters, and F is called the corona loss function. It varies with the ratio of Vn by V0. I have told you earlier that this is Vn is operating voltage, and this V0 is the disruptive voltage, and given in the tabular form like this. That is V0, Vn by V0. This is F value. If it is like this, you can take the value of the F, and accordingly you will find the value of the Pc. But usually you will see that irrespective of looking at the values of these, that is limitations, it is this formula which is almost always used to calculate the corona loss. But sometimes if you are asked, and when this F is given, in that case you will be asked to find out the this corona loss by using this formula. Now let us try to do some numericals based on the same thing. Determine the corona characteristics of a three-phase line 160 km long. Conductor diameter is this. This is the spacing between the conductors. Air temperature is this. Altitude is this. Corresponding approximate barometric pressure of 73.14 centimeter. Operating voltage is 110 kilovolt and 50 hertz. Let us try to find out the corona loss first. Let's calculate the radius. Radius is the half of this, that is 0.518 centimeter. The ratio of d by r is this, that is 471. So square root of d by r will be equal to 1 divided by 471, that is equal to 0.046075. Delta is equal to 3.92 b divided by 273 plus t. So given the values of b and t, it comes out to 0.957. Assume the surface irregularity factor 0.85, since in this question it is not given. If it is not given, you should always take it to 1, but here is the question. I have taken it from the book. It has taken itself to be equal to 0.85. So for this value of the irregularity factor, surface irregularity factor, the critical disruptive voltage will be like this: 2.21.1 into 0.85, that is this, into delta, that is this value, into r, to be in centimeter ln of d by r. So giving the value of these values, it comes out to be 54.72 kilovolt line to neutral. So this is the critical disruptive voltage. Similarly, the critical visual disruptive voltage will be given by this formula. So for this MV we are using for the local corona, it will be 0.72. It comes out to be 66 kilovolt. Now calculating the power loss, it will be 241 into 10 to the minus 5 f plus 25 delta into root of r by d into V minus Vd whole square kilowatt per phase per kilometer. Given the values, comes out to be 0.671 kilowatt per phase per kilometer. Multiplying this value by the length of the line, that is 100, that is this 160 kilometer, it comes out to be 107.36 kilowatt per phase. So when multiplied by 3, it comes out to be 322 kilowatt for all the three phases. Now this was the corona loss under fair weather condition, where we have used the actual value of the critical disruptive voltage. Now under the foul weather condition, the critical disruptive voltage will be equal to 0.8 into the fair weather value of the critical disruptive voltage, that is this value, that is this 554.72 value. It is the value of the critical disruptive voltage in fair weather conditions. So in foul weather conditions, taking only 80% of this, that is multiplied by 8.8, comes out to 43.77. So the losses per kilometer will be per phase per kilometer will be, again using the same formula, only thing is this has to be replaced by 43.77. So it comes out to be 3.3875 kilowatt per kilometer per phase. Multiplied by 160, it comes out to be 542 kilowatt per phase, and for three phase it comes out to be 1626 kilowatt for all the three phase. You can see the difference. This is 322 and this is 16.26. So under foul weather condition, coronal loss has a good amount of value. Now let us try to do another similar problem. A three-phase equilateral transmission line has a total coronal loss of 55 kilowatt at 110 kilovolt and 100 kilowatt and at 114 kilowatt. What is the disruptive critical voltage between the line? What is the coronal loss at 120 kilovolt? So we use the same Peterson formula. So in the both the questions you can see that we haven't seen the limitations, that we haven't calculated the R, we haven't calculated this Vp by V naught. So in that case, when we haven't done that, so we are still using the Peterson formula. So this is actually the justification of the reason that we always try to use the Peterson formula irrespective of its limitations. But only thing, when you are asked and when that capital F is given, so when it is specified, then you may be asked to find out the coronal loss by using the Peterson's formula. So here, this is the formula for calculating the coronal loss by using the Peterson formula. So in general, since we are given only voltages and coronal loss, we can take other quantities to be constant. That means F, delta, R and D to be taken as constant. That means PC is proportional to Vn minus V naught whole square, where Vn is the operating voltage and V naught is the critical disruptive voltage. I again specify it because the nomenclature for different books may be different. I don't want you to be confused with this nomenclature. So I again repeat that the first value will be the operating voltage in the square and second value will be the critical disruptive voltage. So for the first condition, it is given that for the first condition, that is 55 kilowatt at 110 kV, it is usually three-phase voltage. So here it is in the formula, it is the phase voltage. So 55 is proportional to 110 divided by root 3 minus V naught. This is equation 1. And then for the second, 100 is proportional to 114 divided by root 3 minus V naught whole square. This is equation 2. Dividing this and this, it comes out to be 55 by 100. That is equal to 63. This is the 110 by root 3 will be this value. 114 by root 3 will be this value, and they will be in the square form. So taking the square root of both the sides, you will get square root of this, that is equal to 0.74, and this remains without square, that is 63.5 minus V naught and 65.8 minus V naught. So after solving for V naught is equal to 57 kV. It is the critical disruptive voltage phase to neutral. Now in second case, this W is proportional to 120 divided by root 3 minus V naught, that is W will be equal to 12069.28 minus V naught square. So dividing this equation by this equation, it comes out to be W by 55 is equal to 69.28 minus V naught, that is this, divided by 63.5 minus V naught whole square, that is this value. So after giving the value of this V naught to be 57, W will be equal to 196.3 kilowatt. This will be the answer for this. So the line to neutral disruptive critical voltage will be this value. So in this case, we are able to find out the value of critical disruptive voltage and the coronal loss for different voltage. Now let us try to discuss about the factors that affect the coronal loss. Actually, we are discussing the parameters which lie or which are in the Peterson formula. So they are usually related to three factors. One is the electrical factor, second is the atmospheric factor, third is the factor connected with the conductor. First, we'll discuss the electrical factors. Electrical factors, we have two types. One is the frequency and the voltage. Let us first discuss about the frequency and the waveform of the supply. We know that this PC is proportional to square root of, sorry, it is not square root. I don't think it will be square root. No, it is not square root. So please correct it. It is not square root. It is proportional to 25 plus f without the square root. So it means the higher the frequency of the supply, the higher is the corona loss. This shows that, this is an important point, the DC corona loss is less as compared with the AC corona loss. But it is not that the DC corona loss will be zero. It will be definitely less as compared to AC corona loss, but it is present there. One more thing which is important regarding this point is actually about the waveform of the supply. Actually, because of the corona phenomena in case of AC, third harmonics are always present. So when corona occurs, it results in the distortion of the voltage waveform, which results in the presence of the third harmonic. Third harmonics mean 150 Hz. And from this equation, you can see that third harmonic corona loss will be more as compared to this 50 Hz, and the total will be more. So hence the corona loss is still large as compared to 50 Hz alone. So it has this disadvantage of that it results in the third harmonic components in the voltage, which results in the additional corona loss. Now field around the conductor, that is, which depends upon this critical disruptive voltage. The field around the conductor, in addition to being the function of the voltage, definitely this field will be the function of the voltage, but it also depends upon the configuration of the current conductors, because field in general will be voltage divided by the distance, and that distance will be depending upon the configuration of the conductors, whether they are placed vertical configuration, delta configuration, or horizontal configuration. For example, if the configuration is horizontal, the field near the middle conductor is large as compared to the outer conductors because of the two conductors which are present in its vicinity close to it. The critical disruptive voltage is lower for the middle conductor, and hence the corona loss of the middle conductor is more as compared with the other two conductors. That's how the field will affect this corona loss. Also, the height of the conductor from the ground has the effect on the corona loss. The smaller the height, the greater is the corona loss, because the field effect of the critical disruptive voltage of the conductor. This is actually for the vertical configuration, and the conductor which is near to the ground, that is the conductor at the bottom, will have higher corona loss because of the lower critical disruptive voltage. Now, atmospheric condition, as we know that in Peterson formula, this PC is proportional to Vp minus V0, which is itself a function of delta whole square divided by the delta. So where delta is this value, the lower the value of the delta, higher is the corona loss. Lower the value of the delta, lower will be the value of the critical disruptive voltage, higher will be the value of this expression. So higher will be its value when it is squared, so higher will be corona loss. One more thing, when we take this individually, when it is lower, because when it is on the denominator, the whole term will increase. In both the cases, it will increase the corona loss. So for lower values of delta, pressure should be low and temperature should be high. You can see it from this equation. When delta is low, it means pressure should be low, temperature should be high. So it is for this reason that corona loss is more on hilly areas than on the plain areas, because on hilly areas this delta is very less as compared to the plain areas. So in hilly areas, corona loss will be more as compared to the plain areas. One more atmospheric factor, that is rain, dust, snow, and hail effect. The particles of dust clog to the conductor, thereby critical voltage for local corona reduces, which increases the corona loss. Because this dust is not actually formed on the conductor uniformly, it may be present certain places and it may be absent on the certain places. And when it is present on the certain places, on that localized place, the critical disruptive voltage will decrease and it will result in the local corona. Similarly, bad atmospheric conditions such as rain, snow, and hailstorm reduce the critical disruptive voltage, and hence coronal loss will increase. Now, the factors that are connected with the conductor. This is the most important factor. So, the diameter of the conductor. As we can see from here, the PC is, I can take the factors individually. PC is proportional to square root of this R, and PC is proportional to Vp minus V naught. Now it is a function of this R. I should have written as R instead of delta. Wait a minute, I will change it over here. It is now R. It's a function of R now because we are talking about R. Now from this, it seems that this as the radius increases, coronal loss will increase as a square root of the radius of the conductor. But as radius increases, the critical disruptive voltage increases directly as that of the radius of the conductor. So the effect of this increasing the coronal loss by the square root of radius is actually nullified or decreased, or we can say the effect of increase in the coronal loss because of the radius, which is square root of radius, is less as compared to the decrease in the coronal loss because of this critical disruptive voltage. So overall, you will see that when the conductor diameter increases, the coronal loss will increase. Sorry, the coronal loss will decrease. So it appears from the first relation that loss is proportional to the square root of size of the conductor. That is from this. That is, larger the diameter of the conductor, larger will be loss. It appears. This sentence is uh, for this parameter only. But from the second approximation, as VO is approximately directly proportional to the size of the conductor, hence larger the size of the conductor, larger will be the critical disruptive voltage. Hence smaller will be the factor this. And this factor is predominant as compared to this factor. It is found in practice that the effect of second proportionality is much more than the first on the coronal losses, and hence larger the size of the conductor, lower will be the coronal loss. So it is deduced from this relation that as the diameter increases, coronal loss will decrease. Now, number of conductors per phase. For operating voltages greater than 380 kV and above, it is found that the one conductor per phase gives large coronal loss and hence large radio interference, because this is one of the disadvantages of the corona, that it also introduced the higher frequency component, that is third order, this third harmonic component, that's 150 Hertz, which result in the radio interference. That means interference in the communication lines. So which is normally run parallel to the power lines. It results in the interference in the lines, power lines, sorry, communication lines, which are very close to close vicinity to the conductors. Now this problem of the large coronal loss is solved by using two or more than two conductors per phase. So in that case, we use the two or more conductors per phase, and those conductors are known as bundled conductors. So by bundling the conductors, the self GMD of the conductor is increased, or we can say radius is increased, and thereby the critical disruptive voltage is increased, and hence coronal losses decrease. So in one of the chapters where we discussed about the bundled conductors, I told you that bundled conductors are specially used to decrease the coronal loss, and it has some other advantages which are over and above this advantage, that is the reducing the coronal loss, that it decreases the this inductance and it increases the capacitance. By doing that, it increases surge impedance loading of the transmission line. So these are the after effects of the bundling of the conductor. There is one more advantage of this bundling of the conductors. It also increases the stability of the system. That will be discussed when we come to that chapter. Now, one more parameter is the profile of the conductor. By this, it means the shape of the conductor, whether cylindrical, flat, or oval. Actually, it is uh, we're talking about actually the surface irregularity factor. So because of the field uniformity, in case of cylindrical conductor, the coronal loss is less as compared to the other shapes. So it is because of that property of the cylindrical conductor, the field is uniform around it, and coronal loss will be less as compared to the flat or oval. And that is why for cylindrical or smooth conductor we take m naught to be equal to 1. When that appears in the equation, critical disruptive voltage increases, that coronal loss will decrease. Now, surface conditions of the conductor. Since the conductors are exposed to atmospheric conditions, the surface would have dirt deposit on it, which will lower the disruptive voltage and increase the coronal loss. We may say these surface conditions are very close to the atmospheric conditions. In that case, we also uh, deduce or conclude that when dirt or some rain or snow are clung to the conductor, critical disruptive voltage decreases, which increases the coronal loss. Methods of reducing the coronal loss. The coronal loss can be reduced by large conductor diameters or hollow conductors or bundle conductors. Usually we use the bundle conductors. Hollow conductors are usually used in case of substations. And large diameters, we don't use them because as compared to bundle conductors, large diameters, large dia conductors are very costly and they have not as much advantage as we have for the bundle conductors. Now, line design based on coronal loss. It is desirable to avoid coronal loss on power lines under fair weather conditions. We usually try to design or avoid the coronal loss only in the fair weather conditions. Bad weather conditions such as rain, sleet greatly increase the coronal loss and also lower the critical disruptive voltage of the line on account of the later effect, that is the bad weather condition. It is not practical to design the high voltage lines which will be corona free all the times. So if we do that, that means if we design the corona or line on the basis of the coronal loss in bad weather conditions, it may be practically uneconomical. So if the lines are designed without corona, even during the bad weather condition, the size of the towers and conductors will be uneconomical. That's what I have told you. Since the bad weather condition in a particular region prevail only for very short duration of the year, the average coronal loss throughout the year will be very small. So that is why we never try to design the line based on the bad weather condition or foul weather condition. We always try to design the line on the basis of the fair weather conditions. Typically, as we have calculated earlier also, the coronal loss for fair weather condition may be 1 kilowatt for 3 phase per mile, and for foul weather the loss may be equal to 20 kilowatt per 3 phase per mile. So you can see this is very high, but since this uh, foul weather condition does not remain, it remains only for short duration of time, so we cannot design, we usually not design this line on the basis of this condition, that is foul weather conditions. So what is the disadvantage of the corona? It is obvious that it results in the power loss even if during the fair weather condition. Even if it is very small, but it still results in some power loss. When corona is present, the effective capacitance of the conductor is increased because the effective diameter of the conductor is increased. The effective diameter of the conductor increases, so it results in the increase in the capacitance. So when capacitance increases, it results in the increase in charging current. These are the three much more we can see disadvantages of the corona, but its prevailing disadvantage is the power loss. Because of the corona, triple frequency currents that flow through the ground, and in case of grounded system, this may give rise to the voltage of triple frequency in an ungrounded system. And as I have told you earlier, this results in the interference with the communication circuits due to the electromagnetic and electrostatic induction effects to that lines which run very close to the power lines. It also results in the audible noise. That audible noise, you may have heard that the hissing sound of the conductors is actually because of this corona effect. So there is one advantage, or we can say one advantage of corona also. It reduced the magnitude of high voltage steep fronted wave due to the lighting or switching, partially dissipating the corona as a coronal loss, because we know that the lighting is a high energy surge, or there may be some voltage or current surge because of the switching. The front, or we can say if we have uh, steep waves, steep voltage or steep current waves, their energy may be lost as a coronal loss, and it may act as a safety valve in that case to some extent. So one more disadvantage is radio interference. It is the adverse effect introduced by the corona on the wireless broadcasting, as I have discussed just before. The corona discharge emit radiation which may introduce noise signals in the communication lines, radio and television receivers. So these noise signals, as I have told you, can be heard as a hissing sound of the conductor. So radio interference is also one of the very important factor while designing the transmission line. So I think this is all about uh, this corona. So I'll stop over here. Thank you.